Yeah, we are live now. Okay, so good evening, everybody, or good morning, or wherever you are in the world. This is one of the preliminary webinars of the Space Renaissance Congress, the fourth World Congress of SRI. It will take place next year from end of June and 4th of July. And I am Adriano Autino. I am the founder of Space Renaissance International, and I'm also the CEO of Space Renaissance International. And today, I will also be the conductor of this webinar because unfortunately our conductor, that is Maria Mocazel, couldn't be present because of her commitments with the job and with university and so on. So, okay, we will do our best. Our guest today is Ghanim Alotaibi. He is from Kuwait, and yeah, I will quickly introduce him, reading his abstract of the presentation he will give today. The presentation is about space-based solar power and a new paradigm of the space industry. The idea of generating solar energy in space and beaming it down to Earth using lasers or microwaves is not new. Isaac Asimov envisioned a large space-based solar power satellite transmitting energy to Earth in his 1941 short story, Reason. Later, in 1968, Peter Glaser described the SBSP concept in greater detail and obtained a patent for it. The concept was further studied by ERDA, ERDA, but by the early 1980s, the project was discontinued. During the 1980s and the 1990s, however, new technologies emerged and several global efforts, particularly in Japan, advanced the technology readiness level of wireless power transmission. In the early 2000s, a study by the International Academy of Astronautics IAA concluded that SBSP concept is technically feasible. This year, new studies have identified 5 concepts with strong potential for commercial viability, and multiple startups worldwide have successfully raised funding to pursue them. In recent years, we have witnessed a new paradigm in the space industry: the sharp reduction in launch costs, the emergence of highly modular SBSP architectures, and the growing global demand for clean energy have positioned SBSP as a promising emerging space market. This lecture provides a concise historical overview and explains the reference SBSP concept evaluated in the 1980s. It then highlights modern advancements and shows how new designs overcome the challenges faced by earlier concepts. A brief review of the most commercially viable SBSP architectures is also included. I have to add that one of our co-founders, one of the 5 co-founders of Space Renaissance International, that's Patrick Collins, living and teaching economy in, well, now he's retired, so he's an emeritus professor of economy at Asabu University in Kyoto, was one of the promoters of this technology in the 90s in Japan. And he worked together with JAXA, the Space Agency of Japan, and with the government of Japan to develop the first concept of the space-based solar power. So we can say that one of our founders is a part of this history, and that's a very nice thing. Okay, about Ghanim Alotaibi. He is a PhD candidate of the University of Strathclyde. His research project is thermal management for an advanced solar power satellite. concept with the aim of advancing the technology readiness level. As a mechanical engineer graduated from Kuwait University, Ghanim started his career as a petroleum engineer at Kuwait Oil Company. After obtaining a degree in astronomy and completed his master's in solar energy photovoltaics from Freiburg University, he proposed the first satellite for Kuwait University. The satellite project was funded and it was successfully launched in January 2023. Ghanim was an active member in many space nonprofit organizations. In the past, Ghanim was the Middle East Regional Coordinator of the Space Generation Advisory Council. Currently, he is the project manager for the Moon Village, participation of emergency space countries. The aim of the project is to bring developing countries to perform moon projects. In addition, Ghanim is a board member of the Space Renaissance International, okay, SRI, and co-chairing the Towards the Young Generation Committee. Ghanim's exposure to space research and the wider space community motivated him to initiate and lead countless activities to bring concepts of advancing human civilization into space to developing countries. For this reason, he founded Advanced Space Civilization Initiative, where he offers courses about the topic for the general audience, focusing on developing countries. So, okay, Ghanim, the floor is yours.
Thank you very much, Adriano. Just a small correction. I know I sent you the bio, but there is a mistake. I am no longer the project manager of the PESC in the Moon Village Association. But of course, I am still in touch with the members there to support the project. So that's a quick update. Thank you very much for this introduction. The topic of space solar power is really exciting, especially in the recent years, and it seems like things are going to be developing really fast in the coming months and years. In this presentation, I really want to focus on how the concept was developed since the reference concept that was realized during the late 1970s and early 1980s, why the project was terminated, and what are the new technologies that made the project technically feasible and also potentially commercially viable in the coming future. So things are really progressing really fast, and I want to highlight those technological advancements. Also, I want to mention that space-based solar power can be a wild card, actually, because it can open the opportunity to expanding humanity to outer space. And this is something we will discuss in the end. So the first mention of generating power in orbit and delivering this power to Earth was by Isaac Asimov in a short story called Reason in 1941. The short story is amazing. It's a discussion inside a solar power satellite generating power in orbit and beaming it down to Earth as it was operated by a human some years ago. But recently, humanity started to build a robot that can be aware, and it can operate this satellite autonomously. However, the conscious and self-aware robot did not believe that those two engineers, as you can see in the picture, invented him. He started to worship actually the energy source in the huge spaceship that is generating power and delivering it down to Earth. A very interesting human aspect in this, but what's really interesting, in 1941, solar energy was not invented, wireless power transmission was not invented, and yet fiction predicted it. The first application for solar photovoltaics was in 1958, and actually it was for space applications by the NASA, and to power the Vanguard project, as you can see. It's a very tiny solar cells, as you can see in the image, positioned at different angles to receive solar irradiance. Although at that time, by the end of the 50s, there was no solar simulators to really characterize solar cells precisely, it seems the efficiency was around 7 to 10%. And now this is really low compared to what we have right now. More recently, Redwire installed 34% efficiency solar cells in the International Space Station, and we will talk about this very soon. Wireless power transmission, as we know it now, was born in 1964. Now, before that, there was advancement in radar communications, and there was also the idea of transmitting power by Tesla. But really, point-to-point power beaming was born in 1964. And the efficiency at that time was not more than 50%. The first demonstration was only transmitting 4 watts DC from 2 points. At that time, the technologies existed, and this is still, by the way, exist, magnetrons and klystrons. And as you can see here in the timeline, since 1964 until 1975, the increase in efficiency was really dramatic, from 50% until about 82%. And in 1975, as you can see here in the picture to the top right, the Venus site, at the Venus site, you can see the dish here, which is the transmitter, beaming power to the antenna in the scale of hundreds of kilowatts, 450 kilowatts. And the efficiency, 82%, is really astonishing given the small time frame of developing this technology. So in 1968, as the solar photovoltaics was demonstrated in space and wireless power transmission was also demonstrated in the ground, Peter Glaser came up with a detailed description about space-based solar power. And this picture is from his patent that was obtained in 1973. So he proposed the concept in 1968, but he obtained the patent in 1973. So as you can see, in the top, the umbrella-shaped array here is basically photovoltaics, solar photovoltaics. And at that time, monocrystalline silicon did not exceed 10% of efficiency only. Solar irradiance will be converted from to DC current through solar cells, and then the DC current will be transported over this entire length until the transmitter, and the wireless power transmitter will convert the DC current into microwaves that is beamed down to Earth. In the ground, there is a rectifying antenna, as was demonstrated earlier in the 60s. This rectifying antenna will receive the microwave beam and transfer it to electrical power to the grid, so to feed the grid. As you can see here, this is a mechanically steered transmitter to choose the location of Earth that can be that is pointed to. This satellite is located in a geostationary orbit, and Peter Glaser actually, although the efficiency at that time did not exceed 10%, he was proposing that the system will have 40% efficiency solar cells. And of course, he was talking about futuristic prediction. He thought that the efficiency will reach 40%. He also mentioned that in order to manage the temperature on board this huge satellite, cryogenic active thermal management will be required. And this is another technical difficulty, not only at that time, but also today. Power management and distribution is also technically challenging, and the entire system is huge. But it's really interesting, and I quote from his patent. This is what he mentioned in his patent. Power from the sun is not a new concept. However, up to a few years ago, it has been treated as a more or less scientific curiosity or as an energy source, which is of more academic than practical interest. More recently, however, the space program has undertaken to use solar energy for power aboard spacecraft, and the use of solar energy to generate a sizable quantity of electrical power appears feasible. Now, the technology was immature at that time, and it's really interesting to see how people like Isaac Asimov and Peter Glaser actually thought about the future and how we can utilize space-based solar power. As we know, there is a huge need. There is also a higher awareness among the public that we need to use renewable energy. The emissions, CO2 emission and human population are growing exponentially, and it's important that we move forward to solar energy. Now, for terrestrial photovoltaics, solar energy, the penetration in the market, the total power generated from solar energy only is about around 1%, near 1% today. This is really small and insignificant. Now, compared to solar power from space, we can see huge differences. First of all, the solar irradiance in space is like 30% higher than the standard test condition in the ground. And beaming power from solar power satellite can actually be base load, so 24/7, regardless the weather condition, regardless the cloud, regardless the dust. Also during the night, if we have a solar power satellite located in geostationary orbit, and there are other concepts, as we will see, solar power from space can exceed solar power, terrestrial solar power, with more than 10 times what we can get. So this makes a business case, but of course, this business case really depends on the launching cost. So this is quick number that I made to compare between base load terrestrial photovoltaic plant compared to the size of the retina. So we want to see how much size of base load terrestrial photovoltaic plant, and this means we have to install batteries. Those batteries will be operating during the night and during the days where we have clouds to feed the grid. So quick calculation, and this is based on Kuwait solar irradiance. You can see here, if we have a solar, if we have a solar photovoltaics to deliver 2 gigawatt, it will require about 55 kilometers square. This is not base load. This only delivering power during the daytime. And the worst case scenario in Kuwait, the night is 14 hours and the daytime is 10 hours. Adding the batteries and assuming the batteries will be operating for 4 days, without the need of power. And this is, of course, not feasible, but this is just an exercise to see the differences in sizes. The required area for this virtual photovoltaics plant is about 600 kilometers. However, the rectifying antenna that is in the ground, gaining the same amount of energy, the same amount of power, which is 2 gigawatt, is about 19 kilometers square. Now, of course, the rectangle size also depends on the orbit, the location, the distance of the satellite. This calculation is based on geostationary orbit. So there is a business case here, but the question is, what is the launching cost and the mass of the system that will make this business case viable? So after Glaser's patent, in 1976, from 1976 to 1980, the Department of Energy and NASA conducted a study, and they came up with the reference concept. And this is what I'm going to describe in the next slide. They found out that the cost to the first power was expected to be about 330 billion US dollars. The assumption was to have a manufacturing facility in orbit, in geostationary orbit, and to have hundreds of astronauts working on manufacturing this satellite. There are some technical challenges that I'm going to discuss right now, and therefore the project was cancelled. So it's not only the economical challenge, but also the technical challenge at that time. However, it was recommended to reassess the project after 10 years from that time. So in the early 90s. This is a picture of the reference concept that was considered in 1979 during the study. As you can see here to the right, you have the photovoltaics arrays right here. This photovoltaics arrays tracks the sun. You have a mechanical rotary joint that is linking the photovoltaics array with the transmitter, with the wireless power transmitter. And the wireless power transmitter will be pointing toward Earth. So you have movement of the tracking of the photovoltaics plant, and also you have another movement, different degrees of freedom movement of the wireless power transmitter. The wireless power transmitter, of course, will be beaming power down to the retina. As you can see the sizes here, 10 kilometers times 5 kilometers in orbit. And the requirements of manufacturing facilities in geostationary orbit. Now, this system is monolithic, so it's not modular, as we will see later. And we will discuss the differences shortly. Now, one of the main problems, you have this rotary joint, about the scale of 10,000 volts will be passing through this single joint right here, to be DC power, to be transmitted, to be converted to microwave and transmitted. And this is indeed technically challenging for the thermal management. 10,000 volts power management and distribution is another problem, is another technical challenge for this concept. So, and at that time, solar photovoltaics efficiency was really low. Crystalline silicon, gallium arsenide cells were about 12%, maybe 12%. So the economics of this concept was also not really promising. That's why it was decided to be terminated. I would like here to recall a quote by Albert Einstein, and this is I took this quote from John Mankind's book, The Case of Space Solar Power. It's a very important reference if you want to learn more about the physics and other concepts. There is not the slightest indication that nuclear energy will ever be obtainable. It would mean that atom will have to be shattered at will. One of the greatest mind, of course, couldn't really envision nuclear energy, but it became reality after that. So maybe this is the case also with solar power. So in 1995, the Fresh Look study came up, and then this study actually was in the background of the frustration that the space program is not doing well. Now, from the time of Isaac Asimov and his stories, Gerard O'Neill's and The Final Frontier, and the expectations that the future we will have thousands of people by the end of the 20th century, we will have thousands of people living and working in space. In 1995, this was not the case. Until today, this was not the case. So in the background of this, let's say, frustration, the Fresh Look study wanted to study different alternatives. And among those alternatives are space-based solar power. So it was not really a focused study in space-based solar power. It was found that key technologies required to realize space power satellites have been significantly developed. And I'm going to discuss about this in the next slide. What are those technologies? They came up with a technology development roadmap, and they assisted, they examined about 30 different concepts. They studied those concepts. I'm gonna show you one of those right now. In the mid 1990s, the general awareness about the importance of doing measures to protect the environment was really growing. During the first study, by the end of the 70s and early 80s, we didn't have this awareness. So things are changing now. One of the main concepts is the sun tower. However, the Fresh Look study, although find out that the technical challenges, some of the technical challenges can be solved, there are still concerned about the economical feasibility. This is to the right. You can see an artist visualization for the solar tower concept. The solar tower concept demonstrate the modular concepts. So unlike the monolithic concept that requires hundreds of astronauts in orbit and manufacturing facility in orbit to do a monolithic structure, this concept demonstrates that it's possible to manufacture everything in the ground and launch it using conventional launching platforms. So as you can see here to the left, you have the solar arrays, the circular shape here. Those solar arrays track the sun. Power will be generated, and it will be passing through this backbone structure. It will be collected down to the wireless power transmitter. Now, one of the key technologies that developed during the 90s and was mentioned in the Fresh Look study was the development of solid state power electronics. So instead of magnetrons and klystrons that was discussed in the reference concept, now we have solid state power electronics that will also help with steering the wireless power generated from the wireless power transmitter. And this is really interesting because now we don't really need mechanical steering as we used to have in the end of in the 70s, or even with the Glaser's invention. This electronic steering can be more practical. However, you have the problem of a single point of failure. So any problem happens within this structure, especially down here, will make this billions of dollars structure unnecessary. It will destroy it. You have also the problem of shading. You have to increase the distance, of course, to avoid this shading, but this will increase the cost of this backbone structure. But as we can see here, there is an important development of modularity and using solid-state electronics to generate wireless power to generate wireless power and microwave, and also steer this beam that is created. Also, another advancement with the modularity is that the high voltage now can be distributed. Those arrays are in the scale of megawatts. So we are not really dealing here with 10,000 volts, but you know, there is a distribution of the power. Another important advancement that came from Japan this time in 1996 is the sandwich module. As you can see here in the picture, this sandwich module will have the solar photovoltaics in the top, and in the bottom you will have the RF elements or the wireless power transmitter. Now, this became possible because we can use solid state power electronics to generate microwaves, unlike the magnetron. So in the top, you will have the DC current generated from photovoltaics, and then over a very small distance, the DC current will be moving, because DC current is really vulnerable for losses. The longer the distance the DC current will pass through, the higher the losses. So the smaller the distance will be, of course, much better. Then you have the RF element in the bottom. So think about it as a pizza box, where you have the photovoltaics in the top and the RF element beaming microwave in the bottom. However, this can add another problem, which is the pointing problem. Now, instead of the solar tower, which is, you know, gravity gradient stabilized, this will be all the time facing Earth, and the solar arrays will be tracking the sun. This is not possible for the sandwich panel. Therefore, we will need to have reflectors, and two reflectors, actually. We will need to have two reflectors to reflect the solar irradiance all the way to the photovoltaics. So this way, we will have base load power. Now, this has solved the thermal management problem. This has solved the high voltage, complicated power management and distribution. But manufacturing a flat, huge reflector is technically challenging. And also, you have the problem of a single point of failure. So anything happens within this structure, we will lose the system. We will lose the entire system. And we don't want to have that, of course, for large scale structure. But the sandwich module really made a revolution in space-based solar power concepts in the coming future. So in 1999, also in the US, they conducted the SSB Exploratory Research and Technology Assessment, CERT, and they came up with new concepts. Now, this is a focused study. And one of the key concepts is the integrated symmetrical concentrator. As you can see here, in blue, you have the photovoltaics, and you have a single reflector. You don't really need to have this flat reflector, which is technically problematic. So you have two reflectors reflecting solar irradiance towards the photovoltaics plant, and then the green circular shape here is the wireless power transmitter. Now, this is like an open sandwich module. You have the problem of high voltage again, but it solved the reflection. It solved the reflection problem. So, in summary, from from the beginning of the conceiving the idea of transmitting power from space to Earth, we have several challenges. The first challenge, and the most obvious one, is we need low-cost space transportation. Now, this is changing right now, and I'm going to discuss about this in more details. We will need highly modular and intelligent system, because you don't want to lose the entire system. If you shoot the system with a machine gun, then only what's going to be damaged are local locations. We need lightweight system, of course. The film reflectors and nanotube structures can solve this problem. Safe and efficient wireless power transmission, regulation of the intensity of the beam, of course, should be considered. High efficiency and low mass PV. Since the beginning of the space industry, we have only monocrystalline silicon of about 7 to 10% efficiency. Now we have 34% three-junction thin film. So the weight is lighter and the efficiency is significantly higher. And by the way, the bottleneck of the efficiency chain of space-based solar power is really the photovoltaics. Everything else is higher than 80%, almost now 80% efficiency, but the PV efficiency is really the lowest. So a small increase in the efficiency of the photovoltaics solar array will be considered as a gain in the system level of the space-based solar power concept. Another challenge is the need of high efficiency and high temperature power electronics. Thermal management is a challenge to control the temperature in this large-scale structure. So we need to have power electronics capable to operate in this environment. And there are a lot of advancement in this domain right now. In the beginning, the proposals were about active cryogenic thermal management, but now all the promising technologies are passive, which is cheaper and simpler to be done. In 2008 and 2011, the International Academy of Astronautics conducted an assessment about space-based solar power, and it was found that space-based solar power is technically feasible. So all the challenges now that we were discussing about, a single point of failure, thermal management, active thermal management, high voltage, have been solved. However, the problem now from 2011 was with the economic feasibility. And let's recall that SpaceX first demonstration of their reusable rocket was in 2009. And if I'm not mistaken, the first commercial contract that they were awarded was in 2011. And therefore, this was not the dramatic loss in launching cost since 2011 was not considered in the first study. Therefore, in 2018 and 2021, the IAA Decadal Assessment Study found that the space solar power has become far more viable than was estimated in the first assessment study, thanks for the reduction cost of launching prices. Only last summer, a study also done by the International Academy of Astronautics and the National Space Society, International Astronautical Federation Power Committee, starting from 2024, they examined 31 concepts, more than 31 concepts, and they found 5 concepts to be economically promising. So now the evolution is really going through the commercialization of space-based solar power. Now they depend on technology readiness and risk assessment, technology readiness level, and research and development risk assessment, different matrices to do this study, and comparing different technologies. And those are the 5 promising concepts. To the right, in the top, you see the multi-rotary joint. This is the Chinese concept. We will discuss about those concepts now in more details. We have the direct illumination sandwich. This is the Japanese concept. This is bifacial direct illumination concept. We have the SBS alpha concept. The alpha is by means of arbitrary large phased array. This was invented by John Mankins, and they have a company in Australia, Space Solar Technology. So this is American Australian concept. We have the solar power limited Cassiopeia concept. This is a concept from the United Kingdom. Cassiopeia stands for Constant Aperture Solid State Integrated Orbital Phased Array. And we have the Leucides concept by Virtus Soil, American company, which is different from other concepts, that it's not located in geostationary orbit. And we will discuss about those now very quickly. The Chinese concept did not adopt a sandwich module. So those are the photovoltaics array, and the photovoltaics arrays tracking the sun. Although it looks like the reference concept, but they have distributed the voltage. As you can see, there is a single joint connecting the photovoltaic array with the wireless power transmitter. But this is, they have divided the DC current and voltage. So this is, of course, better when it comes to PMAD. However, it's still high. So in the reference, it was in the scale of 10,000 volts. Now we are talking about 1,000 volts. It's still high, but much better. We have, of course, solid state, RF elements. So this is not really the magnetron. And this is basically similar as the solar tower that we just discussed, but they just inclined it, so they don't have the problem of shading. But all the power, of course, is in the backbone structure. Now, this wireless power transmitter is 100 kilometers in length. So it's, there are also questions about its feasibility. It's too long. To the right, you have another variant of the Chinese concept. We have the direct illumination sandwich SBS concept, and this is a Japanese concept. Now, the Chinese concept needs, of course, complicated attitude determination and control system. But for the Japanese concept, it's gravity gradient. And it's basically bifacial sandwich. So as I described a moment ago, in the top, you have the photovoltaics, and then in the bottom, you have the RF element. But in 1997, the bottom side, they added another photovoltaic modules. So you have photovoltaics in the top and in the bottom to generate more power. Because, you know, as I mentioned, they are losing maybe 70% of the solar irradiance because they don't have reflectors. So at some particular points, some position, orbital position at some orbital positions, you are losing a lot of solar irradiance because of the angle of incident. This is hyper-modular concept, which means that the power management and distribution, the photovoltaics, and the wireless power transmitters are all separated from each other. By the way, all those concepts are 1 gigawatt. You have the SPS alpha concept that was invented by John Mankins. You can see here to the right, there are two variants. The one in the top is the older one, while the one in the bottom is the newest. You have a gravity stabilized concept now. Those are the reflectors. And as the satellite orbits geostationary, it's located in geostationary orbit, and as it's going through its orbit, whenever the sun is in whatever angle, the reflectors, those are huge reflectors, of course, the reflectors will open to allow the solar irradiance to be reflected from one direction down to the photovoltaics plant. And this is a sandwich module. So the RF elements are beneath the photovoltaics plant right here. Now, you don't need to have tracking systems, but you still need to have intelligent systems so you can open the reflectors to allow the solar irradiance coming. Now, this concept concentrates solar irradiance with 3 suns. I mean, the new one is 3 suns, but the older variant also considered concentration of 5 suns. This adds an extra challenge for thermal management, but it's still manageable using passive techniques. Because it's a sandwich module, it's low voltage, and because it's hypermodular, it's safe from micrometeoroids and from damage, of course. There is no single point of failure right here. So this concept can solve actually many problems, and it can be economically feasible, depends on the launching cost. For the attitude determination and the control of the orbital position, those reflectors can be used as solar sail. Another innovative concept invented by Ian Cash in 2015 is the Cassiopeia concept. Now, this utilizes an innovative idea, which is 360 degrees microwave steering concept. Unlike, the steering actually limit of all the sandwich modules I just described is like 35 degrees. So you can steer the beam for 35 degrees in all directions. However, in the case of the Cassiopeia, this power core can emit, can beam microwave power in the horizontal and over the entire 360 degrees plane perpendicular to you. So it can beam wireless power microwave from the side. And because you have the reflectors, it can deliver base load power. Now, this helical shape, DNA shape, interesting shape, you can see here the layers going on. So you have the solar irradiance reflected, goes through a Fresnel lens. Initially, they were considering hundreds of concentration, hundreds of suns concentration, but now they reduced it to less than that, to 8 sun. So this concept also concentrates the solar irradiance, and it beams it down to the photovoltaics plant, and you have the RF element right here to the left that is beaming power from the side. What's interesting about Space Solar Limited, now one of the big challenges is the capital cost of building a huge structure like this. So one way to solve this problem is to commercialize smaller concepts. As you have noticed, having a solar power satellite in geostationary orbit is the choice of most concepts, because you have almost 24/7 over the entire year, almost solar irradiance. So you will be facing the sun almost all the time, except of course to the times of the vernal equinox and the spring equinox. You will have a small limited time of shadow. So going to lower orbit will expose the concept to go into the Earth shadow, which is something we want to avoid because it will reduce the capacity factor. However, Space Solar Limited, they have the Cassini concept, which is planned to be launched in 2030, and they signed a contract with Iceland to deliver megawatt scale to Iceland, which is a very interesting progress by the Cassiopeia or the Space Solar Limited. Let me mention that maybe thermal management will be a problem, and also the mechanical structure, because you are using here Fresnel lens, and this really need precise solar irradiance, accuracy. Unlike the SBS alpha, where you have a huge solar reflector, here you really need to have precise pointing, and in orbit there might be sources of vibration that will disturb this concept. Lucidus by Virtus Soil, an American company. This looks like the Japanese concept. This is a sandwich module. I mean the Japanese concept I described from 1997. However, it has only a single reflector, as you can see here. And they were able to do a single reflector because the entire satellite will be maneuvering. And what's interesting about this concept, they chose to have Melonia orbit instead of geostationary orbit. So they will need 3 satellites and 2 rectina. Sorry for the typo. They need 2 rectina in the ground and 3 satellites to deliver base load power. In one side, Melonia orbit is lower than geostationary, so launching cost will be lower. The disadvantage of this, they will be repeating the entire subsystem. So they will have another ADSC, they will have thermal management extra. So it's really a trade-off. And we will see how this will go in the future. Of course, they are adapting a sandwich module to beam the power to the ground. SBS as a wild card. Now, launching, as you just mentioned, as I just mentioned, launching most concepts are actually located in geostationary orbit. And launching from the moon to geostationary orbit is cheaper. Maybe having a business case by having a solar power satellite in orbit delivering power to Earth can motivate creating business in the lunar surface by manufacturing, actually moving the manufacturing facilities from Earth to the moon and utilize the lower lunar gravity to manufacture solar power satellite component in the ground, in the lunar surface, and launch it to geostationary orbit. This can expand actually human presence in the moon and elsewhere. So maybe this methodology or this path can expand humanity to outer space. So this is my presentation in general. Last but not least, we will need more R&D, of course, to make space-based solar power a reality. Last week, we had a discussion that investing in F-35 required $3 trillion US dollars. Portion of this can make SBS a reality. It seems like private sector is leading the way for space solar power. Now, from the community, it seems there was a energy space solar power conference last month, and the manager of this conference mentioned in his LinkedIn that the money or the funds collected during the last 14 months for space-based solar power satellite startups around the world exceeds all what was raised in the last history, in the history that I just mentioned. So this is a significant improvement. This means that there is a huge momentum going on for this technology, of course. So thank you very much.
Thank you very much, Ghanim. Quite interesting presentation. And yeah, so thank you for your work. That I see that you are following this thing since many years, and you made great work on that. Yeah, for documentation and understanding what are the different possibilities, the options, and so on. Yeah, let's see if we have some questions or comments from our audience. We have William Snow that is watching from Boston, Massachusetts, and he say that he worked on the SPS in the 70s and was a personal friend of Peter Glaser. Oh, great. And then another message from him, glad to see you covering the newer concepts. Lunar resources can now be considered using QuenchGun launchers on the moon instead of mass drivers. QuenchGuns became the new approach since 1981. And yeah, another comment. I was in charge of building Mass Driver 2 at Princeton and Mass Driver 1 at MIT. New groups working on QuenchGuns presently for the Planetary Sunshade Foundation. So, okay, we have it seems that we have a really expert of this project, this technology and this projects. So, yeah, anything to say about? So, forgive my ignorance. What is the QuenchGun launchers? QuenchGun. It is written QUENCHGUN. A gun should be a kind of a gun. Yeah, from the low gravity of the moon, it's easier maybe to use this kind of launchers than to use rockets propulsion
Yeah,
for.
it's a kind of launcher. Instead of using propellant, of course, you can use
Yeah,
more mechanical means to launch things from the lunar surface.
yeah. It seems to me to recall that Kraft Erike in his papers about the moon industrialization was thinking about electromagnetic launchers from the moon surface, long rail, accelerating and yeah, pushing their their payloads to orbit. Yeah, and yeah, of course, the synergy between the moon industrialization, the moon economy, and the geostationary orbits and so on, it will be key, I think, for this kind of projects too. And yeah, I was thinking. Seems that well, not only you, but all the people that are the designers that are thinking about this kind of project for the SBSP, think that there will be a big market on Earth for the SBSP. But have you also considered the marketing space? I mean, it is logic, I think, to foresee that during the next decades, within this century, most of the industrial development will be outside Earth, because we know that on Earth we don't have many possibilities to keep on developing industrial uh, initiatives on the surface of Earth. So we think that according to the Jeff Bezos plan, just to make an example, the heavy industry will be moved into the geolunar space in orbit at the Lagrange points on the moon and so on. And therefore, I believe this study of the space-based solar power is very important for the development outside. Maybe more than development on Earth. What do you think about what?
In most of the studies I just mentioned, there is a mention and there is an extended study about beaming power from point to point in space, whether
Yes.
in the moon or even to Mars. So, for example, in the last study that came up in 2025, there were 8 different types of solar power satellites. And there is one category just dedicated to assess solar power satellite in the moon, in the lunar surface. Of course, in space, it's preferred to use laser, not microwave, because we are using microwave for Earth. We are using basically 2 different frequencies, 5.8 gigahertz and 2.45 gigahertz, because it can penetrate the atmosphere. But laser can be more beneficial in space. We don't have atmosphere, and the rectangular size can be smaller. So
Can be
yes,
more concentrated, you know, more,
yes.
yeah.
Um, uh, this was also mentioned as a wild card in the SBS Alpha concept studies in 2012, and also in the case of space-based solar power. So yeah, of course, solar power satellites can be used in the moon, Mars, and between satellites as well.
Yeah, so even in hypothetical on-air cities in Lagrange points, for instance, yeah, they can they can be directly fed by solar panels, but they could maybe also profit get more profit having energy beamed from solar power plants only dedicated to generate to produce power, no, and feeding to the customers around in space. Yeah, yeah, that's it. It's very interesting. And yeah, what another question, because yeah, you know that we are in our pre-congressual discussion in SRI, we are also discussing very much about the huge energy requirement by the supercomputers and the big data centers. And since at least 1 year, we have proposed to move the big data center in orbit, where they can be directly fed by the sun, and so that will move outside Earth the energy demand for the big data centers, and also the cooling will be very much easier in space than on Earth. On Earth, you need an enormous quantity of water to cool the big data centers, while in space it will be easier and more economic, probably also. Yeah, for sure. And leaving alone the point of the water consumption, that's another important thing. So seems that our energy demand will be skyrocketing. It is already skyrocketing, but it will be even more. So do you think that SBSP could give a contribution to this energy demand on Earth, and not only, because if we will have data centers in space, they will need to be fed. So that will be another possible client, no, for SBSP.
I personally support launching or delivering human activities from Earth to space. But this has to be in a more business and commercial perspective, so that it assures its sustainability. Now, my discussion was more about the economical viability seems to be stronger and stronger for a single case of space-based solar power. But as I mentioned in my last slide, combining solar power satellite with other potentially commercially business cases can also can facilitate and make expanding humanity to outer space is even faster. So yes, you can have data centers in space. You can utilize some of the solar power concepts, the modular solar power concepts.
Yeah.
For example, to build a huge photovoltaics plant to create a shadow. If you don't want to choose an orbit particular for that. And also you can link it with other business opportunity, business opportunity in orbit, like, for example, harvesting hydrogen from the lunar ice in the poles, and manufacturing propellant in the lunar surface, tourism, and so on and so forth.
Yeah, sure. So interesting, profitable synergies can be evidenced, of course. Yes, when I saw your slides about different concepts of collecting the solar power and concentrating and yeah, making it usable, let me say in a simple with simple words, then for sure that can be used in connection with data centers, with workshops, orbital workshops. Let's think about what it will be, the reuse, the processing orbital debris to produce new raw materials in space, like powder for 3D printing or propellant for rockets and so on. So we will have, no doubt, we will have workshops, and we will have fueling station and some entities, no, in space when we really start industrializing it. And in all of these cases, the technologies that the SBSP is studying and developing, and we hope soon starting to test, because yeah, we knew by Patrick Collins that I mentioned at the beginning that Japan had a project for a demonstrator already many years ago, maybe 20 years ago or more. They had a project, and I don't know anymore if that project has gone ahead or was suspended or what. They also had a agreements with about 10 countries in the equatorial region to have a rectangle on their ground, and so allow the experimentation of this demonstrator. Do you have any news about that?
Unfortunately, no. I also heard that there are passionate programs in Japan. In the 90s, I mentioned the sandwich module, but I don't know any further progress. Of course,
If
there
there
are
was,
many demonstration by Kyoto University, and there are also champions from Japan. But I'm not aware about the the progress on the projects
okay,
they
okay,
planned in the 19s. However, solar power satellite can be a key, uh, because why this is a new paradigm. I think it's a new paradigm because we will have the end user in the ground paying to fund large scale structure in space, and anything will reduce the cost. Any innovation that will reduce the cost of this large scale structure can be a new business case. So manufacturing in space, manufacturing
sure.
high strength, low weight structure, manufacturing, to support the solar power satellite, manufacturing photovoltaics, all these can actually, if they can reduce the cost, it can create a new opportunity. So yeah, satellite, space-based
Great.
solar power can be a key.
We have Williams now. Williams now is giving us some more news about yeah, when about the Ken QuenchGuns. He said these are superconducting launchers that store the launch energy as magnetic energy within the barrel and converting it to mechanical energy. So, okay, it's similar to the concept that Kraft Erike designed many years ago, 40 years ago. And laser system designs were published by the AIAA in the early 80s. And Dana Andrews from Boeing and myself at Princeton wrote the first lunar propellant concept in 1981. he and I were updating that paper, which unfortunately it died before completion. I am continuing. Okay, so my best wishes, William, that you can complete that very worth work. Yeah. Okay. So, okay. If we don't have any other question, or do you have maybe something else to add, Ghanim?
No, actually, thank you for having me. I hope I was able to communicate some of the new concepts. Thank you for the participants, and also thank you for William for joining this presentation.
Yeah, thank you, Ghanim. It was really very interesting and informative, your lecture. So I hope we can do more. And for sure, in our Congress, we can also discuss this point and to have to bring there more information, uh, more news, and we hope positive news about progress of the projects around the world. Okay, so thank you very much, Ghanim. Thanks to the friends that are watching this lecture. The date is now next Monday, the 15th of December, with the Space Renaissance Christmas party. That is the last meeting of the year. We will have Bernard Foing, our president, that will talk about what we have made in 2025 and what we will do in 2026. And yeah, celebrating the successes and commenting possible regressions or what. Okay, we know that 2025 was not an easy year, and uh, okay. Yeah, I am informing the audience because I have a question, very interesting lecture. How can I get presentation? That this video will remain on YouTube, so it can be watched and watched and watched again. And if anybody is interested, maybe to the PowerPoint slides, I think can be requested to Ghanim. Writing him, I will write his address here, Ghanim at space. Okay, I wrote it correctly. Okay, so just write to Ghanim, and I think he will be happy to share
Sure.
presentation slides. Okay, thanks everybody. We'll be waiting for all of you next Monday for our party, end of the year party, Christmas party, and Ad Astra.
Ad Astra. Goodbye.
Bye bye.